That's important. All right. So great to see you folks. Those of you joining online or in person, great to see everybody. And let's see here. Just a little pre-class warm-up to get us started here. As we'll be thinking about C++. But does anybody know the difference between, well, maybe it goes without saying, runtime and compile time in C++? And then what about the difference between interpreted and compiled languages? Just something for folks to think about here. What do folks think here? Or what have they sort of heard? Or what are these, I guess, maybe the better way to ask this is just, has anybody heard of these differences, I guess, between interpreted and compiled languages, or runtime and compile time? We've talked about a little bit in C++. Has anybody heard these terms?
I have heard about compiled language. It's basically you need to, so like for example, C++, then you compile that, turn it into a binary sort of file, so the computer knows what's going on. But I haven't heard about interpreted language yet, so.
In interpreted language, like scripting language like Python, JavaScript, that it doesn't really need to compile the code. There's an interpreter that parsing the code actively, so it's weakly type. As the compiler parse the code, it's doing the execution at the same time, and the type just change whenever it's assigned to a different value or type.
Yep. Perfect. Both of you are right. Right. So compiled like C++ to machine code before we can run, and then runtime sort of what's actively happening. And as you mentioned, for the second point, interpreted. I'll go ahead and put some of these down here. Python and JavaScript are examples of languages that are generally interpreted. People do build sometimes compilers for them that actually compile to machine code. But it is sort of actively happening. In fact, let's see. If you go to your tools, oftentimes you can go to your developer tools in your web browser and see, all the stuff actively happening in JavaScript right there as you load a web page, for example. So that's kind of today's topic, or what today's topic's about, and I'll get into it, is about sort of getting the advantages of programming languages that compile the code like C++, and then the type of languages that are interpreted. So you can write scripts and they're pretty easy to write, and you can change them even while the program's running in that sense. So I sort of call this the $1 million lab or assignment or whatever you want today, so we can make some money. But, this is really the idea with, again, our sort of data-oriented game engines. This idea that now we can actually add not just assets, things like images or these types of things, but actual code is an asset as well that we can add and not have to necessarily modify our engine. So for our assignment, again, I don't have $1 million to give you, fortunate Canadian or US or any amount, I guess. But we're going to make our game engines more accessible with today's assignment, and just kind of learn about how to actually be able to use Python from within our game engines here, which I think is quite exciting. And of course, for your final projects, which I'll talk about in a little bit here, you'll have the option of, you could use Python or Lua or JavaScript. You can choose your own scripting language as you like here. Most folks will do Python, but that's the idea. There's a little bit more to setting this up, but I think I have a lot of setup resources. So that's all I mean by high risk, high reward. So it's a nice challenge, and I think today's assignment will be fun, and we'll get to learn a little bit about it. So with that said, let me get into the course logistics a little bit here. So of course you've got assignment 6 due shortly. So let me open up the calendar so we can take a look at that. So for assignment 6, you're working on your component system. Anybody have any questions about assignment 6 or areas where I can help out?
Yeah, I'm not very clear about the difference between a component pattern and a component entity system. Like, what's the difference between these two?
Yeah, so the way that we're, and let me go ahead and just open up our lab here, or our assignment. So what we have is basically the component pattern here. Let me go, let's see, where is our, or I should say in our assignment 5, I guess, was the game component here. All right, so this basically in this picture is what our component pattern is, adding in components using composition to create your game object. So something of this form that folks are doing. Now with the entity component system, usually the differentiating factor, what makes it an entity component system, and for this, maybe I can open up, I think at the end of this lecture slide, there was a nice talk here. Let's see here. I think I would point folks towards, let's see here. Let me find the exact slide here. Let's see here. Oh, maybe at the very end. Oh, maybe it was in number 6 here, actually. Let's open this one up here. Well, this is the actual exact video here. There's really one or two sort of distinguishing features here, and let me see if I can try to find it here. This video sort of goes through and gives a pretty good idea of what the distinguishing parts are. So again, here's sort of the component pattern. You've got a vector of stuff here. Let me sort of move along here. I think it's around this part where basically instead of storing all of the components directly in the object, you instead have these giant arrays that have the components. So the components aren't stored necessarily in the object inside of its container. They're in this mega array, as it's called here. And then what your game object's actually just holding is a handle or an index into this mega array. That's sort of the distinguishing part, I guess, between a component system and a entity component system, ECS versus just EC that folks often make. And there might even be more of a blur, but that's the basic idea. Does that sort of make sense?
Yeah.
Yep, perfect. Let's see, other questions from folks about homework 5 or 6? What's going on? We've still got a little bit of time for the homework 6, but let me go ahead and I actually want to open that up here. And hopefully, homework 6, I think, is on the lighter side, but hopefully, folks are enjoying it and taking some time to dig into some code here. And you can, we might be at the point where you can actually, I'm just going to kind of flip through this quickly. Yeah, you could start learning from some of your other classmates. So after the deadline, I'll post this on Piazza so we can have more of a discussion. Or someone can remind me to do that, or just do it. But it's kind of neat. Hopefully, once you finish your section, you can look at, the other folks who looked at the same or similar engine. So this is actually pretty cool to kind of look through here and see you folks making some progress here. So there's plenty of slots to be filled. Oh, some folks are taken towards the end. So I hope you're enjoying that assignment there. Let's see, other logistics questions on homework 6 or even homework 5 at this point? Right. not seeing any, so I want to move to the sort of next logistic stuff. So we'll have assignment 7 that's been pushed to your repository, so you should have that ready, and that's going to be on the scripting stuff that we're going to talk about today. And then next week we are going to have an online exam. So I'll update this with the exact date that it's going to open on. And I'll make sure to remind folks on Piazza. This will probably open on Monday of next week. And the basic idea with the exam is there won't be any class next week, so you'll just have the online exam. And there's a little study guide here as well. I realize the link's a little bit hard to see here, but maybe I'll change that color here. So basically the way the exam's going to work is it's going to be open book, open note, open slides. You can use your homework, so you can build a cheat sheet if you want. You can do whatever you want here. You just can't take the exam, with other humans. So, posting on Stack Overflow or something can't be done, or taking it with a friend. The format will be short answer and multiple choice, I'll say. And you'll be given about 180 minutes to take the exam. And again, I expect it'll take about a third of that time. So try to give more buffer just so you don't have to panic. You can take your time, you can have your notes, you can search through your homework code if that's useful. And I'll just make the note that once you begin the exam, you must complete it, i.e. in one sitting. So basically what I'd recommend for folks is, use the regularly scheduled class time or find a block of time when you're normally watching the lectures or whatever. And that's when you'll actually take the exam. All right, so that's on the logistics. The content is basically, more thinking questions. So, you could kind of go through and take a look at some of these topics here. Another way to sort of prepare for the exam is just, kind of go through and just look at, okay, do I understand? If you looked at the outline here, is there anything that looks super unfamiliar? Okay, so that would be sort of the idea here. So you can kind of, again, look through and say, okay, what is a game engine? You might be able to want to define that. And again, that sort of shows up on the study guide. What's the purpose? So you can kind of go through this, build a cheat sheet. I also look at it sort of as a deliverable of the class if you built a cheat sheet or use this as a template. But that's the idea here. Okay, just some of these topics here and a few ideas. I mostly want to know how you think. That's why the exam format will be short answer and then multiple choice. And for the short answer questions, just being able to explain concisely and clearly maybe what a trade-off is, or something about a design question or those types of things. Okay. So that's the exam and the exam format. Any questions on that? Yep. So I'll remind folks again, and you'll have next week to take the exam. And again, so there won't be any class. You'll just have this time reserved for our one and only exam here. And then, of course, the next week after is spring break. So then we'll resume with probably talking about physics and collision stuff. Now, that said, the other sort of logistics and stuff that's going to be happening in the meantime is I'll send out folks a survey for building teams for the final project. So for folks who, and I'll kind of explain how those logistics work, I suppose, but most likely for you Vancouver folks who are live now, you'll have, 2 teams. Based off just, how many folks are there. So they get sort of teamed up. And then for my online folks, I'll try to match you up by campus or other metrics that make sense in the survey. If folks want to opt into a solo project, that'll also be an option. Some folks historically have liked to do the project themselves. But the real end goal of the project is to kind of take the pieces that we've learned and build a game engine and a game with the infrastructure that you build. So that's where we'll sort of be heading. All right, so that's the idea. Any questions about that or those logistics? Yeah, I'll send out a little bit more information, but hopefully that makes sense otherwise. I think that's pretty much it. So again, assignment 7, you'll have your exam next week. And then, yeah, then we'll form some teams, and that'll be the end essentially of individual assignments, and then you'll just kind of have one deliverable for the rest of the course that you'll be working on. Now weekly, of course, with the lectures and stuff, I might be giving you some code to play around with based off of the topics. So you'll have sort of the support in that sense. But for your project, you might figure out with your team what component system, or if someone built an entity component system, you might use and be able to reuse some of that code as you build out your project. All right. So with that said, though, we'll go ahead and get started. If you have questions about anything, please let me know, or post on Piazza if anything comes up. But what we were working on last time with our sort of, really the last 2 times, and then with our game object study was, thinking about game objects, thinking about data-oriented designs, thinking a little bit about hardware, caches, the importance of how we lay out our data. And again, that was really getting into the component system, or the entity component system, and how we might make them more efficient. That's sort of the idea here. So really this is about the last 2 lectures or so. And then of course you had that game engine study, which you're working on for your homework. So again, use this the engines that you're looking at as a source of inspiration. I think there will be good patterns, and you can see how they're using resource managers and these types of things as well. For today, though, looking at where we're at and sort of the different pieces of a game engine, we're going to be kind of looking at the gameplay foundations, and in particular the scripting systems here. So really we're going to be looking at the things that make a game, I suppose. That'll be the scripts that sort of have the logic and make the game fun. And then some other things that we might want to think about for our game objects, like if they're static in the world or dynamic, and how that might affect things. So let's go ahead and proceed forward with that. And again, it's always worth thinking about, or we're getting into the point of the course where we might start thinking about, and this is something that you'll think about with your teams, what type of game you want to build, and thus what type of games your engine will support. So, it could be a more platformer style game, or, some other type of, some of you might wander into doing 3D. Some of you might want to do more arcade style games or racing style games in 2D or whatever. So that'll be something we have to start thinking about. So I have to talk just a little bit about gameplay. And again, we're sort of focused on the technology here. But again, every once in a while we have to talk about some games here. But the reality is, in this course, or at least I'm approaching it as training you folks to be engine programmers and technical. But the users of our game, they don't really care what technology we use. In fact, I can't think of a game that I've played and I've said, oh, this was in C++, I enjoy it better. Or this was in JavaScript. Usually I have no insight into what programming language or languages were used. You could probably guess all console games are in C++. That's pretty much true. But it doesn't really matter to the end user or someone who has a non-technical background, right? Which is a lot of the user base here, right? The gameplay is always sort of king here. So this is an older game by somebody at one time I knew who made a Geometry Wars or a version of it. And I've just sort of highlighted that, if you look at the reviews of this game, it's relatively simple. I would argue the visual style is very nice and it's clean, but its reviews are very positive, right? And this has sold thousands or maybe hundreds of thousands of copies, or maybe millions even for this particular title now. But then there's sort of the other end of it, a game like BioShock, which you can tell has huge teams. I think these are, 200 plus people teams, if not more, which also has, about the same amount of very positive reviews. Both games are well regarded, but you can just kind of tell, the style's different. At the end of the day, it just sort of matters, is it fun? Is the story compelling? These type of things. So that's just kind of the point I'm making when it comes to gameplay and gameplay mechanics. Right? Thinking about what the rules of the game are, the objectives. Do you present a game player a series of challenges that maybe progressively get more challenging and thus make the game fun over time? And has a good flow of the game. That's what kind of makes a great game, right? Good game mechanics, usually a good narrative, or at least a motivation for why you want to succeed, some sort of feedback. That's what makes a great game. So, in thinking about designing the end game and thinking about some of the capabilities, usually you have some sort of plan about how you're going to design things and the individual components. So, of course, we've talked about components and the different types of components that we might need for a game. For example, a sprite, a texture, and then the game object holding on to those. And we might need fonts and user interface and text and all these sorts of things. Those are all kinds of things that we might want to plan and sort of storyboard out here. So, I mean, that could literally be pieces of paper where you plan things, or maybe HTML or some paint program. Again, just some sort of rough sketch. Game programmers or producers might come up with a design document, for instance, highlighting, all the different things that you need in your game. So as you're designing some of those components, whether you're thinking of them in terms of, this is a sprite, this is a texture, this is a tile map, whatever the components are, one of the attributes that you might want to think about is whether it's a static or a dynamic element. And that's sort of what I want us to think about just a little bit as we're starting out here. Because we want to sort of understand just the different components or how to organize, I guess, different components in our game. Again, whether they're going to be static or dynamic. So I'll have to kind of give you a few examples here. But again, the purpose is that it might influence how you work with your actual game object or you structure it. You might have two different types of game objects, or you might have a game object for static things in your world and a game object for dynamic things. Again, just one other idea for how you might want to organize things in your world. So again, what do I exactly mean when I'm talking about something that's static? Well, something like a terrain, usually not changing in most games, buildings, literally a rock. These are things that you don't really interact with in the game. They're more just environmental for, creating the actual scene. Maybe you interact with them in a physical way, meaning, you can't walk through these obstacles, but otherwise they don't really serve any purpose in the game. You can't, pick these objects up and move them, okay? Versus dynamic elements, the main character here, the cars moving around, etc., power-ups that you collect. These are all sort of dynamic elements in a game. Lighting and particles, things that are changing. And I think that sort of makes sense here, okay? And here's just another example. Mario Kart, of course, each of the karts are dynamic. Each of the elements that you're picking up here, or the power-ups, would be dynamic things. It's kind of interesting just to separate these out and to think about in your games the sort of dynamic versus static elements that you have. And there's a nice illustration. This is from the Game Engine Architecture book. And you can see here's the final scene on the top. And then on the left here, here's all the static things that you don't really interact with. And on the right, here's all the dynamic elements, things that can move in the world. So you can kind of see, the main characters. You can even see some of the characters that are, hidden in the scene, but they're there. The cloth, for example, is dynamic because it has, some physics property, or this chair maybe can be moved around or thrown or something. But that's sort of the idea there. Okay. Here's just another illustration. Again, sorry, this image is in black and white, but this is from Tomb Raider. Again, you could just see the difference between dynamic and static elements. One of the differences here, just to give you an idea, and again, a lot of the examples will be 3D here. In the top left image, again, sorry, it's kind of black and white. It might be a little bit hard to see, but you can actually see some of the environmental objects like this statue are actually dynamic, meaning that the character can interact with them, right? They can kind of take cover and hide behind this object. So that's another way just to think about the dynamic elements, okay? Now, depending on the game, you might have a high ratio of static versus dynamic elements. So this is the game Asteroids, where you're a ship here, which I'm sort of highlighting, and you shoot a projectile here, and it breaks these rocks. So basically everything in this game is a dynamic element. The text is changing, the radar here is changing, etc. So again, it's something to think about, or a designer with their hat on might be thinking about, the sort of static versus dynamic elements. Okay. Now, some games, if folks have played more story-driven games, there's sort of a classic series called Myst, these sort of games. And it has, these are all static elements. You're going to see the sort of animated image move here, but it's pre-rendered. So it's basically just playing a movie here to create this effect of it moving. So that's just kind of a little trick that folks will use to either get higher detail in the game or just a different style here. Now, of course, physics-based games feature primarily dynamic objects. And you could go ahead and see this, of course, this is Angry Birds. Most of these objects, right, where this bird hits are dynamic and kind of moving things around. But I think we're going to see a lot more of these types of games. I mean, this has sort of been a trend for a while, that you have more dynamic moving objects. All right. And again, as I'm sort of going through, these examples, and this came up on Piazza at one point here, right? If you know the sort of state of the object, meaning like these birds, can interact with all these dynamic objects, it kind of makes it a little bit easier if you just iterate through, for example, your dynamic game objects versus having to iterate through all of your game objects, right? The ones that might be static. So again, you can think about this as another way to sort of optimize in your actual game loop what work you're doing, right? We don't need a update loop for maybe the static objects, right? They're just sort of maybe drawn to the window. That these sort of optimizations can happen in our game loop as well as just literally inside of our graphics card. For those of you who have taken graphics programming, you actually get to specify, is this geometry static? Is it dynamic? Can it be streamed in? So some of these different properties. So this sort of distinguishment as I'm talking about static versus dynamic objects is as much an organizational thing that we'll think about from a maybe object-oriented design and thinking about static game objects versus dynamic as much as an actual optimization in our hardware. So just something to keep in mind. I think folks, again, a good chunk of folks, I know my Vancouver folks have used Unity 3D. So has anybody kind of flipped or, seen on like a rigid body, change dynamic to static or something like this in the user interface? Maybe, yeah. I forget what it defaults to, but this is just what I captured here. But you can actually sort of say, hey, this, object's dynamic, meaning that it could change or it can rotate versus is it just a, plain bounding box or whatever. So that can kind of give you some more properties or more power depending on what you're doing. Now, of course, that comes at a cost. If you have more moving objects like shown here, because, well, then your physics processing, takes longer. Okay. Anyway, so that's the idea. Now, of course, I've been sort of giving examples of game objects and these sorts of things moving, but again, this sort of static versus dynamic property applies to other types of entities or components in your world, meaning lighting. So here you can see this character moving around and the lighting's being, calculated based off of where they move. So you can kind of see where the shadows are being drawn. But of course, you can also pre-compute these shadows. And I have a 3D example that is kind of a little bit easier here. If you look at the top left image, that's without any lighting. But in the top right, you can use this trick where in a 3D tool, you pre-compute the lighting, and then it'll look like it has shadows. There's actually no computation going on, but if you saw this in a game, you probably wouldn't notice the difference, right? It seems realistic enough on the right that there's, lights here. It's being simulated. This object won't update, but it gives a little bit of a better effect here, okay? And then you can see another example of 2D where the lighting's baked here, and there's a light source in the middle here, and it's just casting shadows here. So oftentimes that can be another trick here. So some more tricks with your game objects, this time with a sort of hybrid approach here with your game objects. And, we can have basically this object here that you'll see fall over. It's dynamic in the sense that the character can interact with it. But once it's been interacted with once, it's actually a static object now. So you could imagine the actual component being maybe removed, or this object is replaced with something that's static, meaning it can't be interacted with anymore. Okay, so of course these having static or dynamic game objects can change at runtime as well. Okay, so this is a kind of common trick here. So again, it could be a little bit blurred, but it is something that we want to think about, and maybe some more power that you want to add to your game objects. Again, this sort of distinguishment of making it a static or a dynamic game object. All right. So let me pause there for a moment. Any questions on this concept or this new idea that's been added here? Just thinking about static versus dynamic. And there's really, from an implementation side, you could think about creating an actual game object, two different game objects that are derived from one, game object base class where you have a static and or a dynamic one. That's fine. Again, it's just something you'll have to maybe think about if you want to make this distinguishment. All right. So if there's no questions there, I want to talk just a little bit about high-level flow of our game world data as well. Again, kind of focusing on gameplay systems and giving you some ideas of how we're sort of putting together a game at this point in our game engine. And these are the sort of technical terms, but a world is built out of chunks, whether you want to think about that as chunks of data or just a world chunk. That's often, again, how we break up the world. And you can kind of see, here's chunk 1, here's chunk number 2. And, for 3D games, I suppose you could see how this makes a lot of sense because, well, we just have a lot of data, so we just can't often store all the data at once. So we have to sort of break our world up into smaller pieces. So again, from a gameplay perspective, we sort of have the illusion when we're playing a game that, this is one continuous world, but, the reality is one chunk is being, loaded behind the scenes while we're in a different chunk of our world. Perhaps this example will make or be more clear here, in the sort of 2D sense, if you've played Mario, right? So you sort of have world 1-1, and then you have world, 4-1, or the secret world, right? -1 here, that you, again, sort of divide the world up into. Okay. So the idea is, especially with these older systems, and is still true with newer systems, I should say, the actual environment that the player is playing in, like in this, top image here, it could be much more rich with detail if you have more of the system that can be dedicated towards, building this one world at a time, or this, smaller subset of the world. So, I mean, it's sort of an open question for you folks, but, do you think early designers, or really any designers, prefer their games to run continuously? Or do you think that they were actually intentionally designing to have, world 1.1 here and then world 2.1 and so on? What do folks think about that? Or maybe do folks have a preference one or the other when they're playing a game?
Like levels more.
What was that?
I said I like levels more.
Like levels more, yeah. It's actually something that you'll kind of have to make a conscious decision about. Is there a rationale, I guess, or for why the preference for levels?
Like if you break your game into different levels, then different level can have different theme.
Mm-hmm.
So like it provides you more I don't know, like dynamics and possibility to try out different things, rather than like, because you are doing open world, we kind of have to like make everything to stay at the same aesthetic like value, I would say. So I don't know. I don't know.
Yeah. I mean, it gives you a little bit. I mean, even looking at these two images, right? You get a little bit of freedom to make a transition, or a harder transition almost, right? With an open world, right, you have to literally model the whole world in a way that makes sense to transition from one part to the next. So, and it really is just a preference, or a something that has to be planned for. How to do this sort of seamless transition. Let me see here. In a way, with the different levels in Mario, at least for the Mario example, in general, this isn't always true, but you sort of have a linear progression in the story, right? Where you go from level 1 to 2 to 3. Then you can have a narrative that's, a little bit easier to follow. Now, I would say games, especially in the last 10 years or so, have played around much more with, even in a level format, letting you do things in different orders or so on. But, so here's an open world format where, again, you're exploring the world, but you have a different topology, literally with the map here showing that you can go in different directions. So it's just something to think about. On a technical note, we have to sort of think about how we load the next level and some of these details. So you're always sort of loading the next chunk of the level. I can't remember, so let me go on Piazza here very quick. Let's go to Game Engines. Did anybody watch the Spider-Man talk by any chance here? Whoops. Yeah, if you get a chance, I can't click the link because then I'll get a copyright or whatever on YouTube. But if you get a chance, watch this Spider-Man video, or at least just a few moments of it, because they talk about how they handle the world chunk system in the most recent PlayStation 5 Spider-Man, right? Where Spider-Man's going around, the equivalent of New York City or whatever, and how they handle that sort of loading of different levels, because they can't load all the data into the world all at once. So it is just something to kind of think about. There's all sorts of little tricks like this. Can't remember if in this class I talked about much, but yeah, if you ever wonder why sometimes in games you find yourself in a windy corridor, or your character is just climbing a ladder that's really, really tall, what's actually happening during that time is they're loading up the next level in the background. So the designer had to sort of chunk the world in a way and say, hey, put this ladder here so that, if we're on a Nintendo 64 or something, it gives enough time for the next level to load without having to use a loading screen for the player. So little hacks like that, thinking about how to sort of chunk or divide up the world here. Okay, and you can see that there's some transitions in this particular example where you have chunk 1 kind of overlaps a little with chunk 2 and so on. And that's where you'd be doing the sort of load as you move from one objective to the other. Okay, so these are the types of diagrams and some of the designs and things built into the engines in a way to sort of work, or rather, I guess the engine sort of supports this style of level loading to start with chunk 1 and then sort of figure out how to transition to the next layer. All right, so that's one way to sort of think about how the data is moving through your engine in your sort of gameplay systems, right? Just loading one level after the other. Maybe it's done very much in a, here's level 1 and a cutoff and level 2 and then, and so on. Or maybe it's a little bit more seamless, like in this example where you can see there's some overlap between each of the different levels here, each of the chunks. But other style games you'll see where you sort of move or progress through the game in a wave style manner, meaning that, this game, this is the environment here, but you're getting different waves of enemies here attacking your castle. And that's sort of, the next level. Okay, so the next style of progression or whatever. So again, you might think about designing a game like this. This is sort of a tower defense game here. But that's just another way to think about different levels as well. Okay, so you have scores, or maybe you get a cutscene or something, or some sort of bonus as you progress in the game to reward the player. But that's the idea. And of course, here's just some examples of cutscenes. I used to always personally look forward to these when you're playing a game and you get a cool cutscene or something for your reward, right? And it progresses the story. So that's just some ideas. All right. So with that in mind, we sort of talked about static world elements, dynamic world elements, and then at least starting to think about how in a game we might divide up our world and load it into these different chunks of static and dynamic elements. Now there's actually tools that exist or that you would otherwise build on a game engine team as a tools engineer to work with these elements. So again, the Unity 3D editor is a pretty good example, right, where you have stuff built in. So here's just some example tools. For example, a tile editor, whether in 3D or 2D, sort of laying out the level here. We've talked about tile maps a little bit. You've played around with them a tiny bit as well in a previous assignment. So we have that. And then there's other world editors, but specifically for games. So of course there's 3D content creation tools like Maya 3D or these types of tools, but some of the popular ones historically, Radiant for Quake. So here's a 3D sort of almost tile-based, almost CAD computer-aided design-like tool. Valve Hammer Editor, another popular one. Again, you can just kind of see how you slowly create the level here. Unreal Editor would be another example here. Just tool for creating things. And again, here's Unity with a tile map editor here. So these are the types of tools that will help support how we sort of build our game. So, historically, the final project for this course or the types of things that folks have built have been 2D platformer style games. That's what I'll sort of base the lectures around in a way to sort of assist folks in building this type of game. But, we want to also be thinking about, well, if I'm building this tool here, it should also sort of support the style of how the game's played. Meaning, you know, if we're truly building an open world game where there's no loading screens, then our tools should support that so that we can build that world and never have a load screen. But if we're just building, you know, tiny levels, like maybe this is all there is in a game here. This is one level here. This is the map that this character is playing in. That's fine. And then you just sort of export out this map, and that's your data. All right. So the goal of our tools or tool support that you'll sort of have is to make it easy to replicate the style of game that you're building, and again be, you know, easy to use, easier than having to, you know, write or actually programmatically create these types of worlds here. And then we'll have to think about, and this is going to be sort of the next portion of the lecture in a moment, how do these tools support us, whether us as programmers or the artists on our team or the designers, to build new types of objects. So I've actually got a pattern for this called the type object pattern. We'll get into some code here, but we want to be able to, from these tools, be able to create new types of objects that we call prefabs. And prefab, let me actually add the, so prefab means prefabricated game object. So just something that's already been made here. But you'll see the definition prefab in most editors, just so that's clear. Right. Oh, and here I have it. Okay, good. I try to be careful with definitions, but here we are. So here's an example of building a, I don't know what they're building. Oh, some weapon or something here, I guess. But it's got all the textures on it. It's got different models. The different lights are all attached to this one game object. Okay, it's a game object with all of its components ready to go. All right. So let's see. So with that said, just a few more notes here. Again, the features of a world or, you know, tile editor or whatever, some supporting tool, is to help you create chunks in the world here. So, you know, there's a nice video here if you want to create and see that this is the actual image here, but of creating different chunks in the world. So here is literally one chunk, and then, you know, somebody would design another chunk and sort of connect it in this game. I'd encourage you to click this during the break when we take in a moment, and then you'll actually see why this is sort of a unique example. We might also have in our game world editor different layers. You can see the different layers that are being clicked on here to draw, in effect, the draw order. There's, of course, different properties from the game world editor that you might have, whether that's just the position of something or how you're scaling the world. Usually there's tools to help you with placing objects. So here you can see they sort of snap to grid so that it's easy to align things as you're building the world. Of course, there's different types of objects. So we've got some different object types here. And then at the minimum, you know, your tool should be able to save and load levels relatively easy. So here they're creating a game. Breakout is the game here, the game where you have a paddle and a ball bouncing around and you try to hit these bricks. But you can see that they're creating the level editor here, which is quite nice. But you should be able to, you know, export that out and then reload this same level so that you can edit it further or whatever. All right, and then most game editors these days to support sort of rapid iteration. Again, Unity 3D is a good example. Unreal is a good example. Usually you're within or can quickly jump into the game from the game editor. So, you know, when we sort of resume after the little break that we have with spring break and the exam, we're going to be building a little tile editor, or again, that's what I'm going to, you know, help folks with throughout the lectures or use as a running example. Again, there's no reason we shouldn't be able to just jump into the game right away. So here's an example of that with another tool called Kodu. And again, as I mentioned with Unity 3D, All right, you can see we're designing the world in the top window, but you can just hit play at any point and actually test this out. And that's a super, super useful feature to a user. I think it's why Unity 3D, or one of the reasons why Unity 3D is very popular. When I started programming, I was doing it all in code, and that's, save, compile, test, and then repeat. It's too many steps. All right. So let me just do a quick check here. Let's go ahead. That's probably actually a good stopping point for a break here. Let me move our break slide here because we've been going for about an hour. Any questions on the general ideas? Because our next real deliverable, or the next thing that I'm going to have us start focusing on is building some of the tools to support building data for our game engine, and ultimately build a game at the end. Any questions on these tools? All right, I'm not seeing any. So let's go ahead and take a little 10-minute break here. You can stretch your legs, and then we'll resume at 1:03 Pacific time. All right.
Oh, Professor, I do have a question on the homework. It's more logistic though.
Sure, go for it.
I forgot to use my token on homework 5.
Mhm.
Is that okay if I move it back right now?
Yeah, just shoot me a email and let me know, just in case
Okay.
graders have started using it. As long as, we haven't graded it, that should be fine.
Okay, sounds good. Thank you very much.
Yep.
应该是这个 shader 可以做东西。
曾经小学，那橘子皮的，不经历。
shader 是真的，感觉 shader 好难。
6年前。
我摸一下哦。Professor, are you still here?
Yep, I'm still here. Yeah.
Cool. We are looking at the video link. You put the link on the PowerPoint. The
Oh yeah. Let's.
Miega. I think it's almost like 13 years ago. 14 years ago. Why?
Yeah. This one here.
Yeah. Never got
Yeah.
released. So like, how did they achieve this kind of effect? Did they do it with shader graph or like shader programming or something?
That's a really good question. I need to think about that a little bit.
And
Because
we are wondering, can we learn that in your computer graphic course?
yeah, I mean that'd be a great final project. I mean certainly drawing this we'll learn how to do that. The transitions, because they're doing something weird with there's actually they're doing like some four-dimensional time travel thing. I don't know exactly what they're doing. I'll have to look at that.
All right.
But there are certainly, the short answer is I think they're just swapping some of the. Well, I need to think about it. I don't know exactly if they're just taking basically two different shapes and then interpolating vertices from one position to the other and doing that in a sort of smooth way. It's a pretty cool effect, though.
Yeah. It is.
Somewhere there is another video about it. These folks got interviewed, and I don't know if they actually finished this game. I think they just like kept working on it, but at least last I looked, I think they had been working on it for like 4 or 5 or something, some crazy amount of years.
More than 10, I think. Because
More
I
than-
remember I saw this when I was in middle school.
Oh wow. That's too funny. Yeah. Yeah, I mean it's something it's something we haven't talked about, but the scope of our project, right? We can't work on it for 10 plus years. That's too long.
True.
Yeah. As cool as it is, there has to be you have to call it, sometime. Yeah, very cool. Yeah, glad you folks are watching this.
云字自信怎么样？可以。
我那个画就是美术的。
Alrighty, folks. So we'll go ahead and get started here. But I was just kind of searching around, just to try to answer this question about, how this video is working. It looks like there's a few nice lessons here, and they kind of talk about whatever the technique is for how they're doing that warping of the geometry. So it looks like there is an answer in here, which is great. So I'll have to study this a little bit longer, but this would be a great, this looks like a great final project or something for graphics. It looks like it's achievable. All righty. Let's see. Any questions before we get started? Talking about kind of the next, well, we're going to talk about a design pattern here in a moment. All right. Well, let's go ahead and resume. Just a quick recap on, game objects and some of the different things that we've talked about, meaning, well, so far what we've talked about today is some of the different game mechanics, static and dynamic game objects. And then, of course, we've sort of reviewed or seen this in the previous two lectures. A game object is something that consists of, a mesh, sprite, lights, particles, text, user interface, all these different things. And of course, we can implement this with a component system. And I think we're familiar with what a game object is, right? So here are just some examples in Pac-Man, right? All these different things are game objects, but of course, they'll have different properties associated with them. Now, the thing to consider, though, with our game objects, and I know there's a bunch of text here, but I'll explain just from the title here. When we have our game object, again, since we're getting into or starting to think about the tooling side of things in our game engines, there is a distinguishment between how our game objects work, meaning at runtime when the game's actually running, versus the tool side. So actually, one of the best ways to think about this, and again, sorry to keep hopping back and forth, but it really is with this picture here, where the bottom image here is the runtime. This is what our game object's doing, but here's sort of the tool time, right? Our game object. So again, there could be sort of a distinguishment between the tool side game object and then the actual game object as we have here. Now, what do I mean by that? Well, again, it could be a separate game object. You could have a separate game object that sort of has extra information added when you compile a release build, meaning without the -G and the debugging information, so that you can determine, do you want extra debugging information available when you're sort of in the tool or not, which is usually the case when you're actually running your actual game. Okay. So, for Unity 3D, for example, you have a game object and you can change its attributes, while the game is actually running. And you can do that from the tool side. Okay, so that's something that you normally might not be able to do, right? Just, for example, change the character's position to an arbitrary location. That's something you can do in the tool, but again, in the game, if your character jumps or moves up or whatever, that's usually a fixed distance, right? Bounded by the rules of your game. And I suppose I'm answering this question again with this explanation, but if you think your tools could have additional or should have additional functionality beyond what can be done in the games, the answer sort of depends. I would say you could probably include or would want to include extra debugging information, but otherwise be cautious about adding illegal functionality that you couldn't otherwise do in the game, right? Because if you give artists or other programmers or whoever the ability to do stuff that you can't do in the game in your tools, that's something you have to think about as well. It could introduce bugs or unexpected behavior, or you're testing two different systems. So just something to keep in mind here. Okay. So with our game objects, I think we've looked at enough how to sort of structure them in C++. We're now thinking about, could we mark them as dynamic or static? And again, that could be sort of for performance reasons, we want to do that. So we could sort of tag them in different ways and only have to iterate through some. We've thought about our worlds and maybe thinking about how we might want to chunk our worlds together and how that could be useful. And then, of course, we have our logic to actually implement the game here. So here's just some example tools if you want more examples. Game Maker's another neat tool. I would encourage you to look at this link or to click on it again, maybe in the next break, just so you can see some of the tooling that comes along with games. The little sprite editors, little tile map editors. Again, historically, I've asked folks for the final project, you'll build a little sprite animator tool, or someone on your team will, and you'll build a little tile editor. It doesn't have to be anything fancy, but it gives you a nice preview of your character animating, for example. Let's see. And let's say this note here. Assignment. This would be like assignment 8 for us for your final project. But where I really want to get us again is adding a little bit more power to our game objects now with another programming pattern. So we'll talk a little bit about some code here that kind of fits with the theme of, well, thinking about how our games are designed and then getting into the scripting stuff. And what this design pattern is, it's something called the type object design pattern. And what this does is it allows the flexible creation of new classes by creating a single class, and then each instance of which represents a different type of object. Okay. And I would say this is a pretty clear definition, but let's take a look at it. Okay. And we'll look at this in the context of a problem that we're trying to solve, in which you can imagine that you're building a game, maybe a role-playing game. So a game that has, dragons and trolls and orcs and other minions, all sorts of different characters, all these different characters down here. And then each of these characters has different attributes, right? Because they're all different. So they have different amounts of health or magic or speed or whatever attribute that you want to give them, friendliness or whatever. So here's sort of an example code that you might think about for structuring, each of these monsters here. So you have your class for the monster. Usually we make the base class destructor virtual, so that's why that's here. And then you have, some function that you're going to override, like getting the attack for the monster. So again, just a little C++ review, virtual, and then equals 0 means any class that's derived from monster must implement get attack. And then you have this attribute of your monster for the health here. Okay, so that's the basic idea. This is just a base class, or as close as possible in C++ to an interface that you can have. Now, let's say we want to create a dragon or a troll, right? Because we said we want a bunch of different game objects that'll be different types of monsters. So we could have a dragon class that's implementing this base class, or a troll that implements this monster class as well. And then, of course, if we have 50 other monsters, we've got to set up that same hierarchy, right? Or 100 monsters in this case, right? Sort of looks like this, our code, meaning that these are all the little derived classes that you have here, and that might be fine. But what happens if you ask some designer to change the health of the dragon from 50 to 51, or you ask the other designer or whatever to change some value from 37 to 61. The point is, you have to all these little design decisions that you're thinking about, you have to effectively recompile all of your code. Okay. And again, a point of our game engines was to just sort of be these data-oriented, pieces of software that just take inputs and then, they sort of do the heavy lifting of rendering the graphics and controlling the main loop. So, changing all these values in the code or asking someone who's not a programmer to do that and then recompile the software, it's kind of not a good idea. You know, even for someone who does know what's going on, it's not a good idea, right? So instead of using inheritance, right, where you have all these different base classes like dragons and trolls and stuff that implement this monster class, we want to do something more like this, where you minimize your inheritance, right? You just have one base class here, okay? And what Nystrom does, and this is linked on the resources today if you want to read from the Game Programming Patterns book, the type object pattern, is you just create this, you know, breed, whatever type of monster that you have here. And this is what's going to sort of do the work for us, this one singular base class. So the idea is you define a type object class versus a typed object class. Okay. So each type object instance represents a different logical type. Each typed with a D object stores a reference to the type object that describes its type. Okay, well, what does that mean? Let's just see an example here. So all this new classes, or this one singular classes that we're going to define here, that breed here, it's just a container class that contains all the attributes that makes a bear different from a dragon, different from, you know, a troll, or whatever, you know, objects that you have in your game. So you can see that when we create this object here in the constructor breed, it's taking in the attributes health, the attack that it's going to do. So you can go ahead and see, you know, it's just containing these different attributes, again, the health or the attack. In this case, attack is just a string here. Okay. So now when you construct a monster, what you're going to construct it from is that container class here, the breed. Okay. So that's the idea. And again, breed, all it is a collection of data, right? The health and, you know, whatever the attack is. Okay. And then when you want to do the attack, you can see from the monster, it's just calling on, well, the containing data structure here, the breed, which it takes a reference to. That's why it's breed and then the ampersand after it. And then you just do .get attack here. Okay. So you can note, you know, we just set the fields here of health and so on. And then again, do the associated behavior with, well, whatever our container is here. Okay. So this is effectively the pattern that we've created. We've gone from this here, creating all these different derived classes, to just saying, hey, let's make this more data oriented and just include this breed, you know, that's just going to contain some data, and then monster will do the heavy lifting here. So let me pause here for a moment while you've got sort of the code and the pattern on the screen, and see if you have any questions about this. All right, I think this sort of makes sense. So, you know, effectively, to make this data oriented, what you'll want to do is come up with some format for, you know, how do you populate this particular object here. And a simple way to do that would just be to have a, you know, some text-based file that you parse, right? This could be text-based, this could be a JSON file, an XML file, a comma-separated file, right, to spreadsheet or something, where, again, you can see each of the columns are labeling the different attributes here, right? Here's the breed, dragons, bears, trolls. Here's the health, the attack, and so on. So now, if you want to make a change here, and here's the same thing sort of as a JSON file here, right, with each of the breeds here, and of course you can have, you know, different ones. All you're doing is making a change to this file again, or asking a designer or somebody who wants to run a quick experiment to just change the text-based file, and then you just rerun your game and it'll reparse this file, and you know, you get the new behavior. So again, simple idea, but can make a world of difference in terms of the iteration speed, as well as who can work on this project, right? You don't have to have someone who knows how to compile all the source code. Right, a designer, you know, on the game team can actually work on this while you go do engine programming. That's sort of the idea here. All right. So what do folks think about this? Any thoughts, or I'm going to show you the advantages or disadvantages in a moment, but any comments? Does anybody like this pattern? Does anybody see any challenges with it?
I think this will be really easy for designers to make new monsters, but at the same time, it's kind of prone to typos, I think.
Could be prototypos, yeah. I mean, you're hitting on something here, which I'll mention in a moment. But I mean, it is text-based, so yeah. What happens if I put in an illegal value here for 25? I put in some characters. What exactly is supposed to go into attack? I had it here as integers. I was maybe thinking, how much damage, or we're supposed to do here. Here it's sort of a text-based string. Okay, so this is the action that's actually happening. So it could be prone to mistakes. And that is one of the disadvantages. I think it's the first disadvantage I'll show you in a moment, that we kind of lose some of our type checking that we have in the compiler, because we're just reading text here. So we could be prone to errors. That's certainly true. What else? What other thoughts do folks have? Anything? Yeah, let me give you folks some ideas here. I think you hit on some of them here. Or rather, this is where you led me. We do lose the type information. So meaning, we don't know exactly if something's a dragon or a troll or whatever, because we don't have a type system, right? We just have text-based. We have a string here that says this thing's a troll, and that's really it. So now we're sort of responsible for managing that behavior for our objects. Now there is sort of an easy fix for this, in the sense that you're rolling your own type system, meaning that you probably want to include a string or something in this object, and I would call that the runtime type information, to say that, yeah, this is a troll, this is a dragon, or whatever. And then you could kind of, first check to see if someone's defined a legal, capital TROLL for troll or whatever in your system. So you do have to kind of manually keep track of that kind of stuff, and their different types. The second sort of thing that you'll have to think about is, how are you going to define new behaviors for each type? Because with inheritance, if I go back, I'll leave it a few slides to our breed here. What if when I'm doing get attack, I want a different behavior? Maybe some objects can't attack, right? They're friendly monsters. So you got to think about it that way. Or you want more than just get health or get attack. With inheritance, it's pretty easy to add behaviors to your subclasses that might exist, or might be additional or extend the behavior of a data type. But with this, we sort of have to come up with every possibility and maybe encapsulate it in the breed class. So you kind of have to think about, with the type object strategy, you might, if the monsters are going to have wildly different behaviors, you're either going to have to, have essentially a giant switch statement with all the different behaviors that are possible, or otherwise think about in your system how you can, from a text file, add more behaviors. Okay, so that's something to kind of think about. The advantages, though, is, well, it's very easy to define many subclasses. Again, it's just a text file, or a spreadsheet effectively that you're loading and changing things. And then you also, as I mentioned, you don't need to recompile, and you're effectively getting lots of different types of objects with lots of different behaviors. Okay. So again, if you want to add the different behaviors, right, you could imagine having different type objects. There could be smart monsters and flying monsters or whatever, right? And you have these different behaviors that you add different categories for. Okay, so eventually you do have to kind of dive into the C++ code, I suppose, and either define these behaviors, or maybe this is a function pointer that you'll figure out, that has this exact algorithm name for chase algorithm or hibernate or ambush or whatever. And that's how you'll sort of set things up, which again, perfectly reasonable to do. And this is sort of a first version of sort of a scripted behavior that you could have in your game that I think will be neat. All right, does that make sense for folks? Yeah. All right, so let me just show you a few clever design stuff, and then I'll get us into our next section. But this is more on just the editor stuff that I think was neat. Again, just showing on the tool side what you get with a game object. This is something in Unity called a nav mesh that shows what paths a character can take. So you can kind of see these paths here where the character jumps. That's how they get from one block to another. So again, that's just if you've ever wondered how that happens in games, how the character knows to jump or whatever, this is a nice visualization of it where you can see it in the actual tool. So I think that's pretty useful. Again, the idea of being able to visually see updates as you perform them, I think, is useful. So again, here's a live sort of coding example where you can change the code and see what's going on in the editor, or vice versa, right? In this particular example, you're seeing I'm changing the actual output and the code's changing or generating for me. Okay, so that's kind of neat. Same thing happens in Unity, right? When you're creating a game object and it's populated in the scene hierarchy, which we have to talk a little bit about scene hierarchies later, but that's the sort of idea. All right, let's see. I'll keep moving us along since we had our break and get us to our final topic here in a moment. Any questions about anything otherwise? All right, so let me get you prepared for what you're going to be doing for your assignment, which is, again, looping us back to, I suppose, the thing that we should be interested in, the $1 million assignment, and adding scripting. So what we're going to be doing for the assignment is essentially just embedding a scripting language into, well, there's two ways to look at this. You can either embed a script language in C++, or export out our engine so that it could be used in Python. Either or is sort of fine. But just to give you a quick refresher, again, depending on if you've taken a compiler's course or not, some of these terms may or may not be familiar. But again, there's sort of two families of how we generate programs. Again, compiled, you can kind of see from the illustration here, means we take our source code, we compile it down to the machine code, ones and zeros. That's exactly the representation of the program, and then we execute the program and it runs. The interpreter in a language like typically Python means you're just constantly looking at each line one at a time, interpreting what that line does, and then executing it. So that's sort of the difference. And any language could be compiled or interpreted or vice versa, but historically languages like C, C++ are compiled. Languages like Python, Lua, JavaScript are interpreted. So here's just a little bit of a breakdown. Compiled languages are usually a little bit faster because when you're compiling to machine code, the machine doesn't really have to think. It just takes the commands and executes them. It's just literally reading the instructions and following them. Versus interpreted, you have to reinterpret each line at every time that you see it effectively. So there is that sort of slowdown. There's also less room for optimization because the program could be changing as well. So that's sort of the trade-off from performance. But on the other hand, with interpreted languages, you often, even though you're executing slower, you get the flexibility that one, you don't need to go through the compilation step. Typically, you just, hit run or, Python 3 and then the file that you want to run, right? That's been our build script, for example. But you can even change the program while it's running much more easily. So that's sort of another advantage there. So take it with a grain of salt, but compiled languages typically are 10 to 100 times faster. If you're just curious about what the overhead is for compiled versus interpreted languages, again, that's you can write fast or slow code in any language, but that's just a general, choosing the optimal algorithm on C++ versus the optimal algorithm on Python. That's just a general sort of trade-off, I suppose. But it sort of leads to this question for why I'm going to now tell you, well, we're going to add scripting into our games. Now that I've told you it's really slow, at least from a performance standpoint, well, what advantages do we get? Well, the compile time, again, can take several minutes or hours, and that's just the truth of it for a game. So that's changing one line. So it's not feasible in a large game to each time you change a line of code, wait several hours. So time is money in the game industry, in any industry, in life, I guess. So that's just something that we have to think about. And oftentimes, it is actually just more efficient to separate out the tasks that need to be iterated on a lot, like the gameplay, placement of objects, like especially user interface. Again, it just helps make our games more data driven so that we get that fast iteration speed and that flexibility to change things. And then the fourth point is, pragmatically, your game engine just becomes more accessible. We can argue about this, but I would argue Python's probably easier to learn than C++ if you, chose a first language. Both can be used very well, but, if you open up your world to Python or JavaScript or Lua programmers, that's probably a bigger pool of folks who can, use that language effectively in a few weeks' time. So here's just another example of live coding if you want to check it out. I think I've showed enough of these editors, but it shows these sort of advantages of rapid iteration. You'll see in this example, if you watch the video, how you just change code on the right side and it's reflected on the left side, or vice versa. So, with that in mind, we sort of have, again, these sort of two options that we can go with to sort of optimize how our game engines in this course work. So the first is sort of thinking of the scripting language being embedded within the compiled language. And what that means is we'll literally embed Python inside of C++. So there'll be a Python interpreter that reads commands as part of our game loop and executes the C++ functions based off of what's found in a Python script. Okay, so that's one way to do things. Again, the only thing that needs to be changed is the script, and that can happen at runtime or every time that we relaunch our program. Okay, I'll try to show some examples here. The other example is instead, or sorry, this is still with option one, but just to show you what's going on here. And this is with Python again. You have your main program, and then basically what I've highlighted here is you're initializing a Python interpreter, and then with pyrun _ simple string, you'll literally see there's a Python program being embedded in here that's going to be executed, and then you'll see the output shown up. Okay. Now, of course, this example is not very data driven because you have this string here, but you could load a file first and then read from that file or whatever here and execute some commands. So that's the idea here. But the second option is that we can actually compile our engine and export out sort of the main functionality that we would want a user to have. So I've sort of underlined here that a scripting language we would use from Python, our engine as a library here. That's the basic idea. So the actual code that we've implemented has been all in C++. And so that's that means the code's actually compiled. It's in a library, .dll, a shared object file, dynamic library, right, for Windows, Linux, and Mac. So we get that performance boost. Whatever our data structures are, they're all in C++, they're all compiled code, and we just call that compiled code from Python. So that's the idea. Python will just load in our engine as a library and use our code here. Okay, so that's the idea. And then if we make updates to our engine, the engine programmers, recompile our engine, and then somebody from Python can use our code. Okay. So this is the idea here. You would, on the right side here, create this function called spam system, I guess here. Create this object, and then within Python, right? So we'd compile this C++ code into its own module, and then in Python, you say import spam, and then you could call this spam.system function here. That's the idea. Okay. So does that make sense to folks, sort of the two options? Either compiling our engine to a library that can be used in Python, that's this option 2, or option 1 is embedding a Python interpreter into C++, so that we can just utilize Python in our C++ programs. And option 1 actually includes option 2, because you could compile your engine as a library and then make calls to it from Python here as well, which is sort of the ultimate goal. But for the purpose of your assignment, we're going to be doing engine option 2. All right, let me move us along to how we actually do this. So the first thing that we need to do is just choose a scripting language that we want. I'm sort of defaulting everyone into Python, at least for this assignment, because I have lots of examples and I guess experience with it. I have a Lua example as well, but we have to just choose a scripting language. And it's not infrequent that folks will actually write their own language as well for their game engine. I think for folks looking at Godot during the game engine study, it has Godot script, Torque script for the Torque game engine. So it's not uncommon that folks write their own scripting language. Realistically, we have two choices, Lua versus Python. Lua is also sort of the other popular language that a lot of folks use in commercial games like World of Warcraft and other game engines. That's quite common. Python, again, also quite common. And I see it more frequently in 3D graphics tools, for instance, but both of them are good scripting languages that often gets embedded. If you want to see some of the trade-offs between the two languages, there's a little bit of a write-up here on that idea. Yeah, that's, I'm choosing Python for us, so I guess that's all there is to say about it for now. But Lua is an option for your project. You could, I suppose, and I've had one student so far in the times that I've taught this course, they built their own language along with their game engine. So that's an option, right? You can be as ambitious as you want. I say it's unlikely you'll have time in class, but somebody proved me wrong. They did it, so which is always awesome. So that is an option. And actually, JavaScript's another option here. So there's like a couple of choices. But let me talk about PyBind 11, because that's what we'll actually want to use here. I'll just turn my camera off for a moment. So for PyBind 11, the documentation is actually pretty good here. That's the other reason that I've chosen it. So you'll want to, take a stab at reading the documentation, and I've got some videos that'll help you also get started with this. but let me show you the basic idea. So PyBind is basically a C++ library that you download and you wrap your C++ code. And then when you compile your engine, you're compiling it as a shared library that you can then import into Python. Okay, so that's the basic idea. Okay, and it handles a lot of the heavy lifting. Meaning, if I go back here, you'll see that this is actually a really ugly looking code here. This is how you do it with just the pure Python library. But the PyBind 11 API is pretty clean here. So I've got some instructions. I've got some videos on how to get set up with this, so don't worry. But basically, you have to install or set up PyBind 11. You'll have to make sure you download Python. And let me make sure, and the development libraries, which again, I'll show you how to do in a video here. But here's the big idea. As far as this works here, you include the PyBind 11 library. You set up the namespace so you can call the PyBind functions. And then you just write your normal C++ code like this add function here, int I, int j, return I plus j. And then here's the actual wrapping of your code here. Okay, so you say, hey, I want to create a new module. Here's any documentation. And then you just say m.def, and then the function that you want, the name that you'll call it in Python. Address of, that's ampersand add, means it's getting the address of this function. So that's the function. And then, any help description you want in Python. Okay, so that's the idea. I'll run through an example here in a moment. And then when you compile, you're actually going to compile a shared library. And that's how you set up things. Right, so I'm going to compile this example file. There's a little bit more boilerplates here, but I've got some scripts to help you out. And then you can run Python with this module here. Okay. And then here is another example for how you export out classes or structs. Again, same thing, but here's a struct for a pet. And if you want to export out that class or that struct so that's available, you do py class here. And then you say, .def, well, whatever the constructor is, .def set name. And you have a function for a set name, that's a member variable here, and .get name, that's a member variable here, and that's it. Okay, so that's pretty cool. You get the high performance of your C++ compiled code in Python now. Okay, so that's the big idea. And then you can also take advantage of, since you're in Python, any library that you want. Right, if you want to use matplotlib or parse a JSON file or something like that, you just do that in Python, right? Using import JSON or whatever, and you get a list. You get a list data structure. Okay. Okay. So let me go ahead and open up, and let's see if my camera is rusted enough. I'll turn that back on. Let me go ahead and open up this assignment here, just to kind of guide you along here. Let me clone this here. Let's see here. I think I've got this here. Yep, just give me 1 second to do that off screen. Let's see here. All right, so here we are. Okay, so for assignment 7 for scripting, just part 0, what I'm basically going to be asking you to do, and I've got some examples here and here and here that you can look at. And I've got a bunch of examples here as well. So this will be your first step, I suppose, is to, you have some code you can play around with here. But you've got some YouTube videos. So if you're on Linux, if you're on Windows, or if you're on Mac, you can follow along these instructions to get set up. And then here's some more examples on how to actually use PyBind. But let's actually just kind of run through and get the basics set up for you. So again, your goal is going to be to effectively, I've given you a little engine library for this particular example. So again, we're going to build our engine as a library. So you could read about this, and once you have PyBind 11 set up, create some modules. Now, your actual task is with the engine library that I've given is to re-implement your Pong game, except this time you're going to be doing it in Python, okay? And then you're going to be using the SDL functions that you export and implement Python in that way, okay? So let's go ahead and follow the directions here in Engine Library. And it looks like I've given some scripts to try to make this simple. So let's see how those scripts work. Let's cd into assignment 7, scripting. Let's see, there we are. Part 0. And I need to go into the engine library. And let's just see if this works. Otherwise, I'll do another example. Let's see here. I've got Mac build, Linux build. Let's try Linux build here. See if it works. And let's see. Yep, looks like I'm getting a error here. So I might have to change these configurations around here. Let me do which Python 3, which Python 3.6, which Python 3. So you might, and I'm glad this happened, depending on the Python version you have, if you're just running the script, you might have to change this around a little bit. I don't know what defaults folks are going to have. I assume most will have, well, it usually varies a little bit. So let me go ahead and change that here to Python 3.6. And that's if you want to use a specific version. You could probably get away with just Python 3. So you can try that here, but let's go ahead and try that again. Linux build, okay. And okay, something happened. What happened? Well, this is what was built here. myGameEngine.so. So again, I'm compiling here. You can update your version of C++ if you want. But this time I'm making a shared library. Okay, if you're on Linux, that's going to give you a .so file. If you're on Mac, that's going to give you a .dylib file. .dylib. If you're on Windows, it's going to give you a .dll. Okay, something that ends in this. It's going to be my game engine. And then the rest of this should look kind of familiar. We're just including our library. We've got to include PyBind. And then with Python, we're effectively including all of our Python libraries. Okay. Now there's some nice tools for doing this. If you haven't seen, this is kind of a common pattern in tools. You'll get like a config library, and then if you actually run this like this, it'll add all the compiler flags for you. That's actually kind of important to know just for your C++ life, like LD flags or the C flags. Let's see. Oh, it's C flags like this, and then you can see all the include paths here. Okay, so you might see me do those types of things, or let's see, -- includes. Okay, so that way you don't have to type them all out in this giant string here. Okay. Anyways, I'll show how to do that I do show how to do that in the videos, and of course you've got this recording if you need to go back. But anyways, I've made this library here. Okay, so what do we do here now? And let me see what directions I give you. We can try to follow these. Okay, so we run maybe one of these build files, and it generates this file here. And then, well, let's try it out with Python. It looks like I have a little test.py here. And I guess we could run that if we want here. But let me just run it with plain old Python here. And again, let me show you what's in this directory here. This is our engine. And again, I'm not asking you, some of you know Python, some of you don't. That's fine. you'll be able to learn it quite quickly. But let's go ahead and just import my game engine. Okay, so it imported. You don't need to put .so or anything. It just brings it in. And I think if you do help my game engine, let's see what that did for us. Okay, well, our game engine is a library. It looks like that's what I gave us. STL graphics program, that's one of our classes. That should look kind of familiar. That's been in all of our labs. And then if I hit enter, oh, look, there's a method for drawing a rectangle, clearing the screen, delay, maybe that's STL delay, flip, okay, maybe flipping the screen, loop, oh, interesting, okay. And that's it, okay. So those are the functions that have been exported out from our library. Let's go ahead and, now that I've shown you that, let's just go ahead in our source, look at the bindings here. And basically, this should look kind of similar. Well, here's our class. Here's a bunch of functions: clear, flip, delay, loop. Okay. And basically, what we're seeing here is, again, I'm just, and I've got to go down to the bottom here. I'm kind of abstracting or trying my best to take our game loop and export out using PyBind the different functionalities that we might need if I wanted to recreate a game in Python, right? So clear for clearing the screen. Maybe I want a delay function for frame capping. Flip is sort of the function for updating. Let's actually take a look at that. Flip, okay, what's that doing? STL graphics program. Okay, there's a function named flip somewhere. Let's find that. Here it is. Flips to new buffer. Okay, here it is. So that's this function here. Just presents whatever's in our buffer. So anything that we've tried to draw, right? So maybe if we're drawing a line or something, or a rectangle or whatever here, okay? That's the basic idea. Now let's actually try to run our script here. So this is just called test.py. Sorry, let me show you the file for the recording. There it is, test.py. Let's close this out. Oops. So every once in a while I get a little bit wild in Vim here. Quit. Okay, quit out of Python. So let's do Python 3, run our test script. And let's actually see what it does here. Because it happened really fast on the other screen. Sorry, let me run it again here. It brings in this thing and it just moves a rectangle around a bunch here. Okay. Okay, so what's our game engine doing? Well, it looks like I'm initializing our STL graphics program here. And then I print setting up the game loop. And then I iterate 20 times. I clear the screen. I generate a random number here. Again, this is in Python. I'm just generating random numbers. And then I call from our STL graphics program, oh, there must be a draw rectangle function. And then I delay for 100 milliseconds, and then I refresh the screen. Okay. Now let's modify that, because again, that happened too fast. And then I can show you the, again, advantage of writing our library here. Let's modify our Python. Let's do this 100 times. And let's add the delay, half a second. Okay, and now let's just rerun our game here. And here it is. Okay, so every half second, you're going to see there's a new rectangle at a new position here. And actually, as a game designer, I'm not happy with this. I'm going to try to quit. Oh, I can't break out of this for loop here. So here, force quit. Let's see if I can kill it. Or if it crashes. It's still running. It's still going. Just give it a second here. And in the meantime, 1 second here. All right, there it goes. So we can't break out of this loop here. So maybe that's a flaw in our design, but the thing that I wasn't happy about was maybe, again, the size of our rectangle here. So again, I'm just going to use Python 1 to 50 here. And let's change the size. And just so I don't get stuck again too much, maybe every, I don't know, 4 seconds or something, we'll update this. So anyway, you get the idea. Oops, I guess it's, I'm not able to move this around here. Let's see. There we are. So anyway, you can see this little game, or I don't know what to call this. Maybe you could click on it or something. But if I want to add more functionality here into this actual project, I need to go into my game engine, which was in source, just one file, again, for purpose of this, lab, just to show you how to make the engine. And if I want to detect mouse clicks or something, I need to add some function that I can export to handle mouse clicks or, key presses. Okay, so that'll be one of the challenges for you to think about because you're going to be implementing the Pong game, for instance. Does that make sense to folks? Let me pause because I know that was a lot of code, but hopefully, I guess I should wind back and say, does the demonstration make sense of building a library and then being able to use it in Python? Maybe let me start with that portion. Does that make sense to folks? I see mostly head shakes. Let's see. There is some support code, as I mentioned here, just demonstrating, again, with smaller examples. Again, if that's too much to be looking at here, of just, what does it mean to just export out one function? And then you can try to run this in Python. Or if you do like a templated function, how do you use that, for instance? If you want to get into the more advanced stuff, and this is the sort of last YouTube video I have, I show you in Python how to export out your game object. Let's see here. And actually have a, basically how to put the Python interpreter into your project. So you can kind of take a look at that as well. Depending on how you want to implement this. But the overall goal is for you to be able to create in Python a Pong game, okay? I know folks based off of assignment 2 already know how to create Pong. So basically, I'm just looking for 2 paddles and the ability to bounce the ball back and forth. I don't care as much for showing the score or loading in the SDL TTF library. I don't want folks to be burdened with that. I just want them to create something that looks like this. And to do it in a library, because you could figure out the other nitty-gritty details, when you have a team of folks. All right. So let me pause there. Does that make sense for the assignment on scripting? I see some head shakes. All right. So there are some gotchas with this assignment that I've collected. Again, just, building a shared library might be a new idea for a lot of folks. Again, try to watch the videos when you're getting set up that I've provided in the resources section, and try with the smallest examples first, just to make sure that everything's working so you don't get, tons and tons of errors. That's what I recommend. And this will challenge a little bit how you think about your code base. This lab, or this assignment, I should say, meaning that you're kind of developing your objects in a way that, again, if you need to clear the screen, you need to export out a function that lets you clear the screen from SDL. So you might have to break things into small chunks, right? You don't necessarily want to just export one function from your C++ code called play Pong and then just call that in Python. That's not the goal of the assignment. The goal of the assignment, again, is to, export out individual functions and then be able to implement Pong or any other game here. If I see anybody with a one-line script that just calls, play Pong here, that's completely not the purpose of the assignment. And then, of course, as I mentioned, if you don't know Python, you just need to know loops and if statements and how to call your SDL function. That's really it. There's actually really no need to get into anything more interesting with Python, but you can look at a little informal introduction if you want there. All right. So anyways, there is support code, as mentioned. Take a look at the examples. Try the first examples. The PyBind documentation is pretty good. It's well supported. There's been lots of talks on it, so that's another reason why it's being used. Okay, so plenty of support code. And here's just the examples being built. And the main idea, which I showed here, of exporting out the individual functions. And we ran testpy and played around with it a little bit. Okay. And this is just a little bit about the -shared and -f. PIC stands for position independent code. This is how you build a library with your compilers. Let's see, MinGW and MySys users for Windows. This is just some notes. Again, you'll find these in the install videos. And here's just a few notes if there's any common errors. Make sure you're using Python 3, right? We're modern Python developers now. Python 2 is old, so we want to avoid that. And again, you might have to change like version 3.5 to version 3.6 or 3.7 or whatever version that you have available. In general, if you're not sure, you can probably just put Python 3 and it will probably do the right thing, but that's just a note there. All right. All right, so with that said, scripting, there's lots of cool stuff you can get into building these little scripting languages. Again, it need not always be Python or Lua. You can build your own language. Again, Unreal Script is a thing. Godot Script is a thing that you might look at. And again, here's our assignment goal. And just a little note, if you do want to look at Lua, I do have some support code today that's provided. And if folks are truly interested, let me know. Maybe this is something that I could add to over spring break or something, but just kind of let me know if you're truly interested, and then I will allocate the resources towards Lua. But it's just another scripting language you might run into, and I think might be a nice portfolio piece if you. I think PyBind or Lua are going to be great portfolio pieces when it comes to engine development for you to have done and to talk about. But if you want, you can look at Lua. So here's just a few notes on how to use Lua. It's a little bit more involved, I suppose. But once it's working, it's really nice language to use. So anyways, just some notes here. And then I think the final asides, I don't know how well this is supported, but if you love JavaScript, there's something called Quick.js. If you want to, I just recently found this, but you could embed JavaScript into your C++ project. And then AngelScript's sort of the other popular one. All right, so I know that last bit was a little bit of a whirlwind because I'm pushing folks towards PyBind anyways, but you should still be aware that these are other options or languages that exist that often get embedded in the game world, Lua specifically. Let's see. With that said, that's all I've got as far as slides and content. And let me just go ahead and open it up for questions with folks for a little bit here. Any questions from my Vancouver live audience?
So correct me if I'm wrong. So the reason why we are combining a scripting language with C++ is so we can see to save all some of the compiling time, so we can make changes while don't have to directly modify the base code of C++. Is that the reason? Okay. Okay.
Yep, 100%. And it's also sort of, so for folks, I know in Vancouver here, you've done a lot of Unity stuff. The same thing's actually happening in Unity. It's just the scripting language that they're embedding is C# within itself. So we can come up with that same abstraction where you have a script component, for instance, that loads a file or whatever, and then actually runs either the Python interpreter or, again, you just do everything in Python. So yeah, that's exactly the idea, though. It's saving us time and still giving us almost all the performance. Yeah, I think it's important to note, and this is it's on the Lua slide, but it's equivalent for PyBind. We're still getting roughly the native C++ speed. So all of our SDL stuff, all of our graphics stuff that's happening on the graphics card, when we're calling those functions, are still happening fast and compiled. It's just the other parts of Python or whatever that we use are going to be a little bit slower, but in theory, you never have to recompile your engine when you're writing the actual gameplay. Let's see, other questions from folks. Right. Not hearing any questions, so I'll stop the recording here. Let me stop sharing. And then if